In the natural world, form typically follows function. A shark's fin is for slicing through water. A bird's wing is for navigating the air. But what happens when an animal's form presents a stunning contradiction? What are we to make of a creature equipped with hands that seem designed for a nightmare, yet attached to a body that suggests a peaceful existence? This is not a thought experiment. It's a 70-million-year-old case file. The subject, an animal with the claws of a killer, but the body of a herbivore. This anatomical paradox is one of the great unsolved puzzles in paleontology, an evolutionary statement that seems to defy logic. Now let's dissect the evidence and solve the case of this bizarre survivor. Our investigation begins in the Nemec Formation of Mongolia, where in 1948, a joint Soviet-Mongolian expedition unearthed several enormous, scythe-like claws. These bones, some measuring nearly a meter in length along their outer curve, were unlike anything seen before. The initial hypothesis, based on their flattened, strange shape, was that they belonged to a gigantic turtle-like reptile. This is immortalized in the creature's name, Therizinosaurus coloniformis, the reaper lizard, turtle-formed. For decades, this was a fossil in search of an animal. The truth began to emerge not from new Therizinosaurus remains, but from its relatives. The discovery of more complete skeletons of smaller cousins, like Alxosaurus and Bapiosaurus, provided the crucial context. These fossils connected the terrifying arms to a theropod body plan, but one that was radically different from predators like Tyrannosaurus. When we assemble a complete skeletal diagram of Therizinosaurus based on this comparative anatomy, already the paradox crystallizes. Here, let's highlight the features associated with herbivory. Notice the broad pelvis and wide torso, indicating a large gut for fermenting plant matter. The long neck and small skull are also typical of a creature browsing on vegetation. But now, let's overlay the anatomy of the forelimbs. We see powerfully built arms, strong muscle attachments, and at their termination, those three colossal claws. This is the central conflict of our case. The entire chassis of the animal is engineered for a high-fiber, plant-based diet. But it is equipped with weapons that seem grotesquely over-engineered for that purpose. Why would a plant eater evolve hands that could rival any predators? To solve the paradox of Therizinosaurus, we must move from the static evidence of the skeleton to the dynamic reality of the living animal. The question is no longer just what is this, but how did this work? We must conduct a biomechanical investigation to determine the precise functional capabilities of these extraordinary forelimbs. Only by understanding what these claws could do can we begin to deduce why they existed. Let's begin the analysis with the claw itself. The fossilized bone, or ungual, is only part of the story. In life, this bone would have been covered by a keratin sheath, much like the claws of a modern bird of prey or the horns of a ram. When we create a 2D cross-section of the bony core and extrapolate the likely dimensions of this sheath, the weapon becomes even more formidable. The keratin would have extended the length significantly and, most importantly, honed it to a much finer, sharper point. These were not blunt instruments, they were scythes, optimized for slicing or piercing with relative ease. Now, we must place these weapons onto the arm assembly that wielded them. Examining the entire forelimb from the shoulder to the claw tips reveals a system built for power and a surprisingly specific range of motion. Let's use a wireframe model to illustrate the articulation of the joints. While the wrist possessed a fair degree of flexibility, allowing for some rotation, the elbow and shoulder joints suggest a primary movement arc. The arms were not capable of the rapid, complex grasping motions we might associate with a predator trying to subdue struggling prey. Instead, the anatomy is heavily optimized for a powerful drawing or sweeping motion, pulling the arms inward toward the body. To understand the force behind this movement, we can overlay the probable muscle groups onto the skeleton. The bones of the arm and shoulder girdle show large roughened patches where powerful muscles once anchored. These muscle scars, particularly for the flexors that would pull the arm and hand inward and down, are extensive. This tells us that Therizinosaurus was capable of generating enormous force through that specific sweeping arc. These arms were not passive, decorative appendages. They were a highly specialized, powerful biomechanical toolkit. With this functional blueprint, we can begin to test various hypotheses. Could they have been used for predation? The sharpness is there, but the evidence from the rest of the body, the small head, herbivorous teeth, and slow, bulky frame, makes this functionally incoherent. The arms lack the articulation for effective grappling. Could they be for digging? Let's compare the claw's cross-section to that of a dedicated digging animal, like a badger. The badger's claw is short, robust, and built to withstand high torsional stress. The claw of Therizinosaurus is laterally compressed, tall and thin. Subjecting such a structure to the complex, unpredictable forces of digging through earth would risk catastrophic fracture. Similarly, the immense body mass, estimated at up to 5 tons, makes arboreal activity, or climbing, a biomechanical impossibility. Our investigation thus far has successfully ruled out several key possibilities. These were not the tools of a predator, a digger, or a climber. Instead, the evidence points conclusively to a single powerful function: hooking and pulling. The entire forelimb is a massive lever system designed to rake objects towards the animal's enormous torso with significant force. The mystery is no longer about how this machine worked. Our analysis shows it was a highly efficient pulling apparatus. The mystery now is what, in its environment, needed to be pulled with such terrifying force. Our biomechanical investigation has provided a crucial piece of the puzzle. The arms of Therizinosaurus were specialized, high-force pulling systems. We have established the how. Now we must synthesize this function with the creature's ecology to determine the why. This is where we move from mechanical certainty to reasoned inference, evaluating the competing theories that attempt to explain the existence of this bizarre survivor. The first and most intuitive hypothesis is anti-predator defense. In the late Cretaceous ecosystem of Mongolia, a large, relatively slow-moving herbivore like Therizinosaurus would have been a target for formidable predators like Tarbosaurus, a close relative of T-Rex. Let's visualize this scenario. The sheer size and sharpness of the claws would have made them a devastating deterrent. A single, well-aimed sweep could have inflicted catastrophic injuries, turning a potential meal into a lethal encounter for the predator. This defensive utility is undeniable. However, a question remains. Is this a sufficient explanation for their primary evolution? Such metabolically expensive and highly specialized structures rarely evolve for a function that is, by its nature, intermittent. A second hypothesis centers on intraspecific interaction, meaning competition or display among other Therizinosaurus. In many species, exaggerated features serve as signals of fitness to potential mates or as tools for ritualized combat with rivals. The claws certainly would have made for an imposing visual display. Yet, the robust biomechanics we analyzed in Section 2, indicating immense functional power, suggest they were more than just a signal. While display was almost certainly a secondary benefit, it seems an incomplete explanation for the powerful pulling mechanism. This brings us to the third and most widely accepted theory. The claws were primarily a foraging tool. This hypothesis elegantly unites the creature's herbivorous diet with the specific pulling motion of its arms. Let's create a diagram of this behavior. Therizinosaurus, with its great height, could have used its claws as giant hooks, latching onto large branches and using its powerful arm and body muscles to pull foliage down to the reach of its beak. This would have given it access to a food source unavailable to smaller herbivores and those without such specialized equipment. It explains why the arms are built for power and a specific pulling motion, directly linking the weapon to the daily constant need for sustenance. Our verdict, based on the current evidence, is that the foraging hypothesis provides the most comprehensive explanation. It accounts for the specific biomechanical adaptations in a way that defense or display alone do not. This does not mean the other functions were irrelevant. Most likely, the claws evolved primarily for feeding, and this function was then co-opted, making them a formidable defensive weapon and a powerful visual signal. Therizinosaurus reminds us that in evolution, an object can be both a tool and a weapon, its purpose defined by the context of the moment. The case of the herbivore with Freddy Krueger claws is not a simple contradiction, but a masterclass in evolutionary opportunism. Therizinosaurus demonstrates how natural selection can repurpose an ancestral blueprint, the predatory arms of a theropod, for a completely novel way of life, blurring the lines we draw between categories. It is a profound testament to the fact that the fossil record is not just a history of extinct creatures, but an ongoing scientific investigation filled with puzzles that challenge our deepest assumptions about how life works. What is your hypothesis? Do you think the claws were primarily for defense or for foraging? Leave your analysis in the comments below. And if you want to own a piece of this investigation, the detailed 3D model of the claw we analyzed is available for our patrons via the link in the description.